Imagine Earth over 4 billion years ago, a time when our planet was almost unrecognizable compared to the vibrant blue marble we know today. It wasn't a blue marble, but a world just beginning to form, a fiery ball of molten rock slowly cooling and solidifying. The atmosphere was thick and toxic, filled with volcanic gases and devoid of the oxygen we depend on. The geological record reveals ancient pillow lavas and rocks, telltale signs of a watery past. These formations, created by underwater volcanic eruptions, are like snapshots frozen in time, offering a glimpse into Earth's early environment. These unique structures could only have formed underwater, in the depths of primordial oceans that covered much of the early Earth. The presence of these formations is a crucial piece of the puzzle. This evidence irrefutably proving early Earth was wet, a planet awash in vast oceans and shallow seas. Water, the elixir of life, was present in abundance. And remarkably, life emerged quickly, within a few 100 million years of the planet's formation. Simple, single-celled organisms arose in these ancient waters, marking the dawn of biology on Earth. But here's the twist. A cosmic conundrum that challenges our understanding of planetary evolution. Astrophysics tells us the young sun was much dimmer, significantly less luminous than it is today. In fact, it was emitting only about 70% of today's energy, a substantial reduction in solar radiation reaching our planet. If that's true, based on our current understanding of climate models, Earth should have been a frozen wasteland, a snowball planet encased in ice from pole to pole. Such a frigid environment would have been an unlikely, if not impossible, cradle for life. The conditions simply wouldn't have been conducive to the emergence and survival of early organisms. This contradiction is the faint young sun paradox, a long-standing puzzle in planetary science that has intrigued and challenged researchers for decades. This paradox was first formally described by the renowned astronomers Carl Sagan and George Mullen in the 1970s, highlighting the discrepancy between astrophysical models and geological evidence. On one hand, geology provides compelling evidence of ancient rivers, vast oceans, and other liquid water features on early Earth. On the other hand, fundamental physics dictates that with a dimmer sun, Earth should have been locked in ice, a frozen world inhospitable to life. If the sun was indeed so faint in its youth, casting a pale shadow across the solar system, then life as we know it shouldn't have started at all. The conditions would have been too harsh, too cold, for the delicate chemistry of life to take hold. So how did Earth manage to stay warm enough for liquid water to exist, and for life to emerge and flourish, despite the sun's faintness? The answer isn't simple. There's no single, easy explanation that resolves this paradox. Earth is far more than a passive rock passively orbiting in space. It's an active, dynamic planet with complex geological and atmospheric processes. It's a dynamic system with its own intricate mechanisms to regulate temperature, a planetary thermostat constantly adjusting to maintain a habitable environment. The solution is likely a tapestry of interconnected factors, a delicate balance of atmospheric composition, geological activity, and orbital dynamics. It's not a single fix, but rather a complex interplay of various planetary mechanisms working in concert. This is a planetary detective story, a quest to uncover the secrets of Earth's past and understand how our planet defied the odds to become a haven for life. The clues are scattered across time and space, hidden within ancient rocks, fossilized remains, and the faint whispers of the early solar system. Let's unravel the mystery of the faint young sun paradox, and explore the fascinating story of how Earth managed to stay warm enough for life to begin. Imagine journeying back billions of years, to a time almost beyond comprehension. Let's travel back to the Hadean and Archean eons, epochs in Earth's infancy when the sun was a dim adolescent, a mere shadow of its current radiant self. It's hard to fathom a sun so weak, so unlike the life-giving star we know today. Scientific models, meticulously crafted and constantly refined, show the young sun's energy output was only 70 to 75% of what it is today. That's a significant difference, a substantial reduction in the amount of solar radiation reaching our planet. This represents a huge drop in solar energy, enough by all accounts to freeze the planet solid, transforming it into a desolate, icy wasteland. The implications are staggering. Simple climate models based on our current understanding of planetary physics unequivocally state that Earth should have been a snowball, a frozen orb hurtling through space. These models paint a picture of a world gripped by an unrelenting ice age, with average temperatures plummeting below -10 degrees Celsius, a truly inhospitable environment. Yet the geological record tells a different story. We find ancient sedimentary rocks, layered formations that speak of flowing water, and zircons, tiny time capsules within the Earth's crust, that unequivocally prove liquid water existed on the surface of early Earth. This is a critical piece of the puzzle. And then there are the stromatolites, layered fossilized structures built by ancient microbial mats, irrefutable evidence of early life, dating back an astonishing 3.5 billion years. These ancient formations whisper tales of a vibrant, thriving biosphere. Life thrived in these ancient oceans, so Earth clearly wasn't frozen solid. This presents a profound paradox, a challenge to our understanding of early Earth. The faint young sun paradox isn't a flaw in our understanding of stellar physics. The sun behaved as expected. Instead, it's a crucial clue, hinting that early Earth possessed a very different atmosphere and planetary environment than what we observe today. Some mechanism, must have compensated for the faint sun's lack of energy, preventing the planet from succumbing to a global ice age. The real mystery, therefore, isn't about the sun, but about Earth's own ingenious mechanisms for trapping heat and maintaining a habitable environment. What specific processes kept the oceans liquid, prevented a global freeze, and allowed life to not only survive, but flourish? The answer, as we'll discover, lies in the planet's unique and remarkable tricks for staying warm, strategies that allowed it to defy the odds and nurture the first sparks of life. Let's delve deeper and explore those fascinating planetary secrets, unraveling the mysteries of early Earth's climate and the origins of life. When we consider the conditions necessary for life to emerge and thrive on a young planet, the challenges are immense. One of the most critical factors is temperature regulation. How did early Earth, bombarded by a weaker sun, manage to stay warm enough for liquid water to exist? The leading solution to this puzzle lies in Earth's early atmosphere. It wasn't the air we breathe today, but rather a thick, heat-trapping blanket, far denser and more chemically different than what we're accustomed to. This blanket played a vital role in maintaining a stable and habitable environment. Greenhouse gases like carbon dioxide were abundant in this early atmosphere, acting as a primary mechanism for trapping solar radiation and preventing it from escaping back into space. And methane, though it exists in only minor concentrations today, played a massive role in the past, contributing significantly to the overall warming effect. These gases, combined with other factors, created a unique environment that allowed life to flourish. Early Earth's atmosphere was likely supercharged with these heat-trapping gases, creating a world vastly different from the one we know today. The concentration of greenhouse gases was far higher, creating a potent warming effect that counteracted the faint young sun. This was especially true for carbon dioxide, which was released in massive quantities from intense volcanic activity that was far more prevalent than it is today. With no plants or complex life to absorb it through photosynthesis, the CO2 levels remained exceptionally high. As a result, CO2 built up to staggering levels, far exceeding anything we've experienced in recent geological history. This massive concentration of CO2 resulted in a powerful greenhouse effect, trapping heat and warming the planet to a degree that would be unimaginable today. In addition to carbon dioxide, methane, produced by primitive microbes in the early oceans and wetlands, also played a crucial role. Methane is an even more potent greenhouse gas than carbon dioxide, so even relatively small amounts added even more heat-trapping power to the early atmosphere. This greenhouse cocktail, a combination of carbon dioxide and methane, kept the planet warm enough. It was warm enough to sustain liquid oceans, which are essential for the development and survival of life as we know it. Furthermore, the carbonate-silicate cycle acted as a planetary thermostat, providing a long-term mechanism for regulating CO2 levels over vast stretches of time. This cycle helped to maintain a relatively stable climate by regulating CO2 over time, preventing runaway warming or cooling. The rate of weathering, which removes CO2 from the atmosphere, is temperature-dependent. Less rainfall and weathering on a cold Earth meant that CO2 removal slowed down, allowing it to accumulate in the atmosphere. This accumulation, in turn, would warm the planet, creating a negative feedback loop that helped to stabilize the climate. Meanwhile, volcanoes continued to pump out CO2, replenishing the supply and further contributing to the greenhouse effect. This constant influx of CO2, balanced against the removal processes, helped in maintaining the delicate equilibrium necessary for a habitable planet. This complex interplay of factors, this intricate feedback loop, ultimately stabilized Earth's climate over billions of years. It prevented the planet from succumbing to a permanent deep freeze, a fate that could have extinguished any chance of life. In essence, the greenhouse effect, driven by these atmospheric gases, was Earth's first and most crucial defense against the cold vacuum of space, a shield that allowed life to take root and flourish. But greenhouse gases weren't the whole story. Early Earth's moon was much closer, exerting immense gravitational forces. This created massive tides and tidal heating, internal friction that warmed the planet from within. Recent research suggests tidal heating was a significant energy source, especially in polar regions. It worked alongside the greenhouse effect, helping keep oceans from freezing. The Earth-Moon dance may have been vital for life's survival. The young sun was dimmer, but also more active, blasting out a stronger solar wind. This wind shielded Earth from galactic cosmic rays, which are thought to seed clouds. Fewer cosmic rays meant fewer clouds, lowering Earth's reflectivity and letting more sunlight reach the surface. Less cloud cover meant more warming, helping offset the faint sun. This subtle effect made Earth a more efficient solar collector. The interplay between solar wind, cosmic rays, and clouds added another layer to Earth's warming strategy. It's a reminder that even small changes can tip the balance. What if life itself helped regulate Earth's temperature? The Gaia hypothesis suggests the biosphere acts as a self-regulating system, maintaining conditions for life. Early microbes produced methane, warming the planet. Later, photosynthetic life drew down CO2, cooling it as the sun brightened. Life created feedback loops, producing greenhouse gases when cold, removing them when hot. This biological thermostat kept Earth's climate stable for billions of years. Life wasn't just a passenger, it was a planetary engineer. The faint young sun paradox isn't just Earth's story, it shaped Mars and Venus too. Mars once had rivers and lakes, but with less solar energy, it needed an even thicker greenhouse atmosphere. Mars lost its atmosphere to space, becoming a frozen desert. Venus, under the faint sun, may have had oceans and a temperate climate. As the sun brightened, Venus hit a tipping point. Runaway greenhouse effect boiled its oceans away. Water vapor trapped more heat, creating a vicious cycle. Solar radiation split water molecules and hydrogen escaped, making the loss permanent. Venus became a hellish world, showing what happens when climate regulation fails. Mars froze, Venus baked, Earth alone found balance. These planetary fates highlight how fragile habitability can be. Earth's unique combination of factors kept it just right. The paradox is a lesson in planetary luck and resilience. There's no single answer to the faint young sun paradox. Earth's warmth was the result of multiple mechanisms working together. A supercharged greenhouse effect was the foundation, with tidal heating and reduced cloud cover adding crucial warmth. Life itself evolved to help regulate the climate, adapting as the sun brightened. Each factor nudged Earth away from a global freeze. The solution is synergy, geology, astronomy, and biology in harmony. That's how Earth stayed habitable against the odds. The faint young sun paradox isn't just ancient history. It's a guide for the future. It teaches us how planets can stay habitable, even under challenging conditions. This knowledge shapes our search for life on exoplanets, showing us what signs to look for. It also reminds us how delicate Earth's climate balance is. The same greenhouse effect that saved early Earth now threatens us if pushed too far. Understanding the past helps us protect our future. The paradox is a story of resilience, luck, and the preciousness of a stable climate. Solving it deepens our appreciation for the world we call home.